Today we're going to look at the second part of the magnetic force on a moving charge that's moving through a magnetic field, and that's going to be how we actually calculate the force. So the previous lesson we looked at the right-hand rule, all right, to determine the direction, and if you note, there's three things that are perpendicular to each other. There's magnetic field direction, there's QV, or we could say current, and then there's force. Okay, so today we're going to see how we calculate that force. So let's look at what we already know. So what do we already know? We already know that the force depends on the magnetic field strength. We've seen that in some demonstrations. The strength of the charge and the velocity of the charge. So those are three variables that we have to somehow have in an equation. We could do this experiment, but it could get a little bit complicated. All right, so I have a pretty cool apparatus that a friend of mine gave to me. It's probably from like the 60s or 70s, and I haven't been able to get it work, but we actually have an electron that travels around, and we can find this relationship using that apparatus, and I've actually done that this lab in college too. So here's the nice thing about all of this. It actually comes out, as many things in physics do, a really nice, clean, straightforward equation. A lot of the greatest equations in physics are very simple. E equals mc squared, F equals ma. All right, this is another one. Force equals BQV. All right, really, really simple, really nice, really clean. All right, so all we do is we take the magnetic field strength in Teslas. We got to be in Teslas. The charge of the object in coulombs, and velocity in meters per second. These are all our standard units for these variables. And we multiply them together, and voila, we get force in newtons. So let's look at an example problem. So example one, the first half of the page are just different applications of the right-hand rule that we already learned. You can try those. I believe there's a solution. I know there's a solution on my website online, and I also believe there's a video that shows how to do those. I'll have to go back and double check that. So if there's not a video that goes through each of those examples, I'll actually make one for you. All right, so if you haven't done those yet, don't worry about it. Let's concentrate on calculating the force for today. So what do we start with? We have a positive charge, okay? That's 0.65 coulombs, so Q equals 0.65. It's moving to the right at 60 meters per second. So 60 meters per second, and we said moving to the right. So it's important that we also not just note what the velocity is, but what its direction is. So moving to the right, all right. And what's the next thing? We have a 0.25 Tesla field that's downward, and this time I say downward, I'll always put like into the page or out of the page, because I don't want you to think down means to the bottom of the page. All right, so downward would be into the page. And when we looked at right-hand rule, we learned that something going into the page, all right, or going away from us is an X. It's like an arrow that, say you're standing on a dock and you shoot an arrow into the water. The last thing you see is the tail of the arrow, all right, and that's the arrow going away from you, okay? So we've identified all the variables. We identify the equation. The physics part of this calculation is done because now all the rest is just some math. So we substitute everything. We have my B, 0.25, Q, 0.65, and 60 meters per second. And we get 9.75 newtons. So that's the easy part of this. All right, so let's look at the more difficult part, which is applying the right-hand rule to determine the actual direction of the force. So I always start with drawing the field. Okay, so here's the field. So let's draw our field lines. Our field is going into the page. So if we draw our field, it's a whole bunch of X's. We have a bunch of field lines because it's a vector field Field meaning there's not just a single vector, there's like a whole sea of vectors. Just like gravity. Gravity doesn't act at just one place in the room, it acts everywhere. So everywhere we could think of gravity acting, we could think of putting a vector in that location. So here's a bunch of field lines going away from you. Okay. The next thing we want to do is plot our next known piece of information, which is the velocity. The velocity is going to the right. So there's our velocity, QV, right? Charge times velocity. These two things will always go together, and that's going to the right. So let's start out how to do this. So what I want to do is I want to point my fingers in the direction of the field. So fingers mean field. All right. So I'm going to take my fingers and I'm going to literally point my right hand so that my fingers are pointing at the computer screen. If your paper's down on the desk, you would point your fingers down into the desk. All right. So I'm pointing straight into the computer screen. Okay. So that's the field. Fingers are field. Fingies field. All right. Now the QV, the direction of the velocity, has to go in the direction of my thumb. Now I don't move my thumb. I keep my thumb and my fingers at a right angle, and I physically rotate my hand around and rotate my hand so that my thumb is pointing to the right. So now I have fingers pointing in the direction of the field into the page, a thumb pointing straight to the right, and now we know the force comes out of our palm. So my palm should be facing toward the top of the computer screen. Boom, there we go. Palm, top of the computer screen. So we've used up all three of our dimensions. This is actually one thing where you have a 50-50 chance at getting the right answer. Because how can we do that? Well, 66% of the information is already given to us. All right? Or I should say 2/3 of the information. Yeah, that's 66%. Duh, Striz. Okay, so what do we have? We have the field going into the page. Well, that's one of our dimensions, in and out, toward or away. We have our velocity going to the right. That's another one of our dimensions, either right or left. Well, what's the third thing that's left? Up and down, toward the top of the page or toward the bottom of the page. So you got a 50-50 shot at that. All right, in this case, it's toward the top of the page. All right, example number 2. Again, a positive charge of 0.9 coulombs. All right, moves to the north at 250 meters per second. So there we go, 250 meters per second. That's the velocity, that's a vector, so I got to include the direction with it. Enters a magnetic field of 0.15 teslas to the east. 0.15 teslas to the east. Okay, so let's do our calculation. So our calculation is BQV. Nothing fancy there. All right, so 33.75 newtons. All right, so let's draw our diagram. When we have a problem that gives us the north, south, east, west, that's called cardinal coordinates. Never eat soggy waffles. We usually draw the diagram like we're looking at a map. Normally when we look at a map, we orient the map so that north is toward the top. All right. Okay, some of you that might have orienteering merit badge would differ, but let's just look at from the most common thing is, you pull out a road map, we orient it north, south, east, west. Okay, let's draw our diagram according to that. So what do we have? We have field to the east, to the east. All right, so we've already used up left and right. QV, QV going to the north. North is the top of our page. So we've used up and down. So we know our force has to either go into the page or out of the page. All right, so what I'm going to do is I'm going to take my arm and I'm going to extend it to the right. Okay, so I'm pointing my whole arm to the right. All right, now my fingers are pointing to the right now. So do that. Get your arm and your fingies pointing to the right. Next, you want to point your thumb to the top of the page. So if your thumb is pointing to the top of the page, all right, which way is your palm? Your palm should be pointing into the page. Boom, force into the page. All right, so there we did. There we did. Really great English, Striz. So there we go. We have left and right used up and down used up. Or a better way to say that is top of the page to bottom of the page used up, and into the page and out of the page is our only options. All right, our second force on a moving charge is when we have force on a wire, which we've seen happens. We already know that because Oersted's experiments and different things that we've looked at in the lab, we get forces on wires. I think I did that demonstration. Yes, I did. The guy that did the demonstration with the big magnet and everything at the beginning of the last video. So from our experiences, we know that we also get a force on a current carrying wire. So let's look at what's different. We start with the same equation. Hey, force equals BQV. That's the great thing about physics again. Once we've learned something, we can use it again. All right, so here we go. Since we already know velocity is length over time, right? If I go 100 meters in 10 seconds, I went 10 meters per second, which is velocity. All right, we can make a substitution into the above equation. So we can say BQ is velocity, which is length over time. So force equals BQ, length over time. Well, we can also rearrange this. Since all this stuff is just multiplied by each other, we can arrange this as B times Q over L divided by time. So I just took this Q, moved it up in there since all this stuff's multiplied. And lastly, we can also rearrange the equation so that now that this being, or Q and L are up here, I could move the L down to here if I wanted. So I got B equals Q over time times L. So it's all just algebra so far. All I've done is looked at, instead of velocity, I'm using length over time for velocity. Nothing fancy there. So let's move on. So this is where we left off on the last page. Well, what do we know about charge per time? We did that last unit. Charge per time. How about charge per time is equal to current, electric current? So now we got another really simple equation. Force equals BIL. So magnetic field strength, current in the wire, length of the wire. Everything else is exactly the same. All we've done is we replace QV with IL. QV and IL are the same thing. IL is just that the current is constrained to the wire. All right, instead of QV, which is some charge moving through space, like the charges that are coming to us from the solar wind and hit our magnetosphere. All right, and they get deflected based on this equation, BQV. All right, the force on a wire gets deflected based on this equation, force equals BIL. Force equals BIL right there. Okay, so let's do one last example, and it's a wrap for today. So we have a 1 meter long wire, 6 amp current. Current's moving to the left, and there's in a magnetic field of 0.35 Teslas toward the top of the page. So here we go. I used that top of the page this time. What is the magnitude and direction of the force on the wire? Okay, so here we go. Length, current to the left, and B is up, top of the page. Force is BIL. B, 0.35, I, 6 amps, length of the wire, 1 meter. I guess I could have used something different than a meter to make the problem a little more interesting. So we multiply the three together. Boom, 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 2.1 newtons. And lastly, let's do our diagram. Well, let's go back to what I said before. So what do we have? We have something moving to the left and something moving up toward the top. So left and right is going to be used up. Top of the page to bottom of the page is going to be used up. So this better be either into the page or out of the page for the direction of the force. So let's see what we get. So B to the top of the page. I pointing to the left. So your finger should be pointing to the top of the page. Your thumb should go to the left. And what do we get again? We get a force going into the page. All right, so all these examples had force going into the page, probably because that's the most easy thing to do, or the most simple. But we could have, if I switched the current around to the opposite direction, we know that the force would come out at the page. So do that for just to prove it to yourself. We've already seen that when we reverse the current, the direction of the force reverses. So if you're pointing your fingers to the top of the page, top of the computer screen, the IL to the left, all right, your palm is facing into the page, which is the direction of the force, all right. Rotate your hand so that your palm is now facing toward you, all right. So now your thumb is pointing to the right. The force is coming out at you, and that would reverse the direction of the force. All right, so now that we have both parts of this force on a charge or moving charge in a magnetic field, all right, we can put this all together. So we have one lesson on using the right-hand rule to find the direction, and now we have a lesson on how to calculate the force. And the rest of this unit, we are going to just look at different applications and what we can do with magnetism. We're kind of done learning new content about magnetism, and so we got about a week's worth of stuff to just look at what we can do with magnetism now that we know some of this.